So in this video, we're going to look at some radioactive decay and how to not only recognize which type of decay we're looking at, but we're also going to try predicting some products. So talking about alpha decays, the first one we talked about in the Chapter 9 PowerPoints, that is the release of a helium particle. Remember, it has a +2 charge, and then it also has a mass of 4, that being the mass number up here. And then this 2 is the number of protons. Okay, so alpha decay is releasing one of those heliums with a mass of 4, 2 protons, and a +2 charge. So because these alpha particles are so large, they are slow moving, and it does not take a lot to stop them. But what we're going to look at today is what these reaction equations look like when alpha decay happens. Okay, so here we have uranium. So remember, these are nuclide symbols, so I'm just going to draw off to the side here just to remind you what a nuclide symbol is. It's a representation of an isotope. This X is the element symbol, in this case U. Up in the top left-hand corner, that is the mass number. And then in the bottom is the atomic number, or the number of protons. Okay, so if I look up uranium on my periodic table, I will see that its atomic number is 92 because it has 92 protons. The mass number I wouldn't be able to figure out from the periodic table because the periodic table gives the average atomic masses, which is different than the mass number represented here. All right, so if I have alpha decay, what that means is how I recognize this type of reaction equation is the fact that I have one of those heliums on the product side. So that is an alpha particle, so I can now recognize this equation as an alpha decay. All right, well, let's move on and see how do we predict. So you not only need to be able to say, okay, I see that we're emitting an alpha particle, so this is alpha decay, you might also need to predict one of the products. So in order to do that, we're going to use those mass numbers and those atomic numbers to figure it out. So what we're looking at doing, if I'm trying to figure out what this other product is supposed to be, what's going to happen is I know I'm going to have a nuclide symbol. Okay, I'm going to have my protons here and then my mass number up here. But to figure out what the proton should be and what the mass number should be is that these added together should equal 235. So both these mass numbers added together should equal 235 because we need consistency on both sides of this reaction equation. It has to be equal, much like balancing an equation. You need the same amount on both sides. Same with the protons. So 2 plus however many protons this mystery nuclide symbol has needs to equal 92. Okay, so to figure that out, we can just take, so let's start with the top. So mass number. What is the mass number of our mystery guy? Well, I can take 235 and subtract 4 from it. Right? So if I subtract those two, it's going to equal what the mass should be of my unknown component. So 235 minus 4 gives me 231. Okay, so now I know my mass number. Mass number isn't going to help me identify what element I'm talking about, though. What's going to help me identify the element I'm talking about is the number of protons. So that's what I'm going to figure out next. So remember, adding these two together on the reactant side should equal 92. So to figure out what this mystery guy is, the number of protons, I will take the 92 from this uranium and subtract 2 from it, which is the number of protons on that helium atom, and it'll tell me what the number of protons of the mystery element should be. So 92 minus 2 gives me 90. So I'm almost done. My last step then is to figure out what is X, what is the mystery element. So to figure that out, I can use the number of protons. Remember, the number of protons identifies the element. If you change the number of protons, you are changing the identity of the element. So I go to my periodic table and I look up number 90. Number 90 is thorium. It is represented by TH. So now I have predicted what my other product should be. Notice if I take 90 plus 2, I get 92. If I take 231 plus 4, I get 235. So it all checks out, everything's balanced on both sides. All right, we'll do a few more of those, but I want to talk briefly about the other two kinds of decay and how to recognize those as well. So with beta decay, so beta decay is the next one. So looking at beta decay, how do you recognize it? Well, it's loss of an electron. So that means you're going to see this symbol with the representing an electron on the product side of the equation. So remember, an electron, 0 mass. The charge is -1. Okay, so if just seeing this on the product side tells me this reaction is representing beta decay. So that's the first step. Now we're going to do some examples where you're predicting the products as well, but I wanted to show an already written out example to show exactly how that's done. It's very similar to up here. So we're going to take these numbers, added together, should equal 11. The mass numbers, 24 and 0, added together, should equal 24. So let's double check and make sure that's happening. So we have 24 plus 0 equals 24. Yes. Okay, 12 plus a -1, so that means you're really just subtracting 1 from 12, equals 11. Correct. Okay, well let's look at why that is this way. So if you can remember the definition of beta decay, you're not only losing an electron, the reason you're losing an electron is because a neutron is being converted into a proton. So what you're always going to see in beta decay is this number of protons increasing by 1. So protons are going to increase by 1 from reactant to product side. So notice it went from 11 up to a 12. Well, how do you know it's magnesium? Because this 12 here, the number of protons, will tell you that. You can look up the number 12 on your periodic table, and it is magnesium, Mg. Let's look at positrons next. So positrons, it's kind of the opposite of beta decay, right? Beta decay, we have a neutron changing into a proton. That's why the protons are increasing by 1. But for positron, we have a proton now changing into a neutron. So what we're going to see here are the protons decreasing by 1 from the reactant to the product side. And notice, reactant side, we have 15 protons on phosphorus here. Product side, we now have 14, so 1 less, because 1 proton was converted into a neutron. And since mass number is equal to protons plus neutrons, the mass number doesn't change at all. Because we didn't take away any neutrons or any protons, we just changed one into another. So the mass number is staying consistent. You can also check that by doing the same thing we did up here. So these two numbers, the protons added together, should equal whatever's on the reactant side. So 14 plus 1 equals 15. Check. Okay, now for the mass number, 0 plus 30 equals 30. Check. All right, so now we kind of know the differences here. We have alpha particle, we have beta decay, losing that electron, changing 1 proton is increasing. So we're changing a neutron into a proton. For positron, we have this positively charged E, which is representing a proton because we're losing a proton because we're changing a proton into a neutron for this one. Okay, so we're going to see that proton number decrease by 1. So now let's try to predict some products. So I'm going to start with this guy here, neodymium. He is 144 and 60. Now I'm going to say, predict the products if this is an alpha decay. Notice all I gave you was the reactant. Okay, well I said it was alpha decay, so you automatically know what one of your products should be. It should be an alpha particle. Okay, and you're always going to have two products. One product will be the particle represented in each of these, and then the other one you can predict based off of that particle. So for alpha decay, we know we have one of these helium guys. Okay, well what is our other product going to be? And remember, to figure that out, we're using these numbers. So the protons, so this 2 and whatever this mystery proton is, added together should equal 60. These mass numbers, the one of the mystery element and of this helium, added together should equal 144. So to figure that out, we subtract the mass numbers from each other, and that will give us the mass of the mystery. We subtract the protons from each other, and that will give us the protons of the mystery. So let's try that. So for mass number of the mystery element, we're taking the 144 minus 4. That's going to give us 140. For the number of protons. So now we're looking at the bottom numbers. So to figure out the mystery element, we subtract those two. So we have 60 minus 2, and that gives me 58. So let's just double check. 58 plus 2 equals 60. Yes. 140 plus 4 equals 144. Yes. So this is all correct. Everything's balanced on both sides. I'm not done though, because I can't leave this as an X. Now that I know the number of protons, I can figure out what element belongs there, what isotope that is. So looking up number 58 on my periodic table, it is cerium, represented by Ce. All right, so let's try another one. So let's say we have so predict the product and tell me which type of decay is happening. Okay, well first let's start with the type of decay. We have alpha, beta, positron. Okay, well it's not alpha, 'cause on the product side I'm not seeing a helium. Beta decay, we need a negative charge here, an representing an electron. That's not there. What's there is a positive with this E symbol. So that's the proton, that's my positron. So the type is going to be a positron emission. And now I can go and predict my product. Now I can predict my product in two ways. I can do those addition things that we were doing before with the alpha decay, or I can use my knowledge of the definition of positron. So positron says that I'm changing a proton into a neutron. So that means I'm losing a proton. So the product is going to have one less proton than the reactant has. So what is 1 less than 5? It's going to be a 4. Okay, because I changed a proton into a neutron, so I have 1 less proton now on the product side, so that's how I get 4. Now the mass number, that's not going to change, because I took a proton and I changed it into a neutron. And if you remember the definition of mass number, it is protons plus neutrons. Okay, so if I take one proton away, but I change it to a neutron, my mass number is not changing at all. So this is still 8. To figure out the symbol, right, I'm using that number of protons there. So number 4 on the periodic table is beryllium. And you can always do a double check. What I mean by that is make sure everything's adding up. So for mass numbers across the top, 8 plus 0 equals 8, check. 4 plus 1, plus a plus 1, right, is equal to 5, check. All right, let's try another one here. So we have so this next one, we're going to predict the products, and we're also going to say what type of decay, what type of emission is occurring. Okay, so I have my one isotope on the reactant side, it is decaying, it is emitting an electron, that's what this E-1 is, and then I'm going to predict the other product. So this E-1, is that alpha decay? No, otherwise we'd see a helium. So it's beta, because beta is that E-1, that electron. So this is beta decay. Now let's predict the product. So to predict the product, remember for beta, we have a neutron now being changed into a proton. Okay, so one of these neutrons out of that whole mass number is going to change into a proton, which is going to add one. So I'm going to always have in my product one more proton than I have on the reactant side. So what is one more than 19? It's going to be 20. Is my mass number changing? It should not change because I have a neutron just changing into a proton. So my mass isn't changing at all. I'm just transferring one into another. Okay, now to figure out what the symbol should be, I'm looking at the number of protons. So I'm going to find 20 on my periodic table, and that is calcium. So I always want to double check, make sure I have everything correct. So I'm going to add my protons and make sure they equal whatever's on the reactant side. So if I have a 20 plus a -1, does that equal 19? It does, because it's really just 20 minus 1. And then 42 plus 0, does that equal 42? It does. So this is the correct predicted product. So when it comes to this chapter, be able to recognize that table that I talked about in the Chapter 9 PowerPoints. So if I say which particle has the highest penetrating power, 0 mass, and 0 charge. Well, that's a gamma ray. So you need to know that table and be able to recognize based off of mass, charge, and penetrating power what particle I'm describing. You also need to be able to recognize, given an equation, if it's alpha, beta, or a positron, and then predict products for alpha, beta, and positron, just like we did here. So the Chapter 9 quiz will really help with that. There will be a few questions on the final exam on Chapter 9 as well. So let me know if you have any other questions.